In early quantum mechanics, we analyze systems using a strictly isolated model. We assume the system is closed, static, and completely sealed off from its surrounding environment. Under this assumption, the total energy of the system is described by the unperturbed Hamiltonian, known as H0. This operator defines the strict architectural rules for the allowed states a system can occupy. The time-independent Schrödinger equation yields fixed energy eigenstates for closed systems. You are looking at a classic s-orbital probability cloud governed by H0. While its phase evolves over time, indicated by pulsing, its boundary, shape, and probability density remain permanently frozen. But physical reality is not an isolated vacuum. Real atoms, molecules, and qubits exist in constantly changing environments. They are continuously subjected to light waves, radio frequency pulses, and fluctuating voltages. We call these phenomena time-dependent fields. Look at the right side of the screen. These fields break the static assumption. When an oscillating wave strikes the orbital, the Hamiltonian itself is altered over time, forcing the electron to fluidly morph into a new configuration. Static mechanics defines the architectural limit of what is possible. Introducing a time-dependent interaction provides the necessary mathematics to calculate how we force a system out of those stationary states. To model this, we expand the equation. The total time-dependent Hamiltonian equals H0 plus V of t. H0 still acts as the anchor. It represents the massive total energy of the native, unperturbed system. The addition of V of t defines the specific time-dependent interaction acting upon that system. In the laboratory, V of t could be a microwave field inside a dilution refrigerator, or a precisely timed laser pulse striking an atomic lattice. Time-dependent perturbation theory relies on one strict mechanical boundary. The interaction term, V of t, must remain weak compared to the unyielding energy of H0. If that condition is met, the math holds. We can calculate the exact probability of an electron absorbing a photon or a nucleus flipping its spin. The V of t operator is the universal language we use to issue commands to quantum systems. How exactly does this mathematics force a quantum jump to happen? If a probability distribution is initially frozen, how does it move? We start by looking at this time-dependent state expansion equation. We write the new, evolving state as a linear combination of the system's original known energy states. Pay attention to the C sub n term highlighted here. This is the amplitude. By introducing the perturbation, this amplitude is now strictly a function of time. Before the interaction, the initial state is at 100%, and all other states sit at 0. Watch the chart as the waveform passes, and the perturbation V of t acts on the system over time. The initial bar shrinks, while the final state bar climbs. The external field is physically forcing these other coefficients to grow. It transfers the probability density across the system's available energy levels. A quantum jump is not an instantaneous leap. It is the calculable, dynamic growth of a target coefficient, driven entirely by the action of the V of t operator. This growth is not guaranteed. Applying an external field does not mean the system will respond. The transition is gated by strict mathematical conditions. This expression in the center of the screen is the transition amplitude matrix element. It is the primary gatekeeper for any quantum transition. On the right side of the bracket, we have the initial starting state of the system. In the middle, we place the time-dependent field attempting to drive the transition, and on the left side sits our target final state. Evaluating this integral measures exactly how strongly the external field spatially connects the initial and final geometries of the system. If this integral calculates to 0, the transition amplitude is 0. The external field is completely invisible to the system. This zero-value condition generates selection rules. It explains why certain spectral lines are completely absent when observing atomic emissions. The math strictly forbids the transition. For light interacting with an atom, the perturbation typically relies on the electric dipole operator. If the transition dipole moment evaluates to 0, light cannot drive the shift. Without a non-zero matrix element establishing a clear spatial bridge between the states, no amount of applied energy will force the system to change. But a non-zero matrix element only establishes the possibility of a transition. It says nothing about efficiency. Look at this diagram. Between any two quantum states, there is an intrinsic energy gap, defined as E final minus E initial. For a transition to occur efficiently, the system must meet the resonance condition. The frequency of the incoming driving field, represented by omega, must correspond perfectly to the energy gap. If the field is off-resonant, the system briefly absorbs and immediately re-emits negligible energy. The probability of transitioning remains near zero. When the field is perfectly resonant, the system rapidly and efficiently absorbs energy, driving the state upward. Resonance provides the exact energetic match that makes the spatial connection established by the matrix element physically actionable. When studying macroscopic materials or continuous emissions, we shift our focus from the probability of a single transition to the actual rate at which millions of transitions occur over time. To calculate this rate under weak continuous perturbations, physics relies on a single foundational formula. This is Fermi's golden rule. It dictates the math behind modern spectroscopy and material science. First, the formula shows that the transition rate scales directly with the square of the coupling strength, our matrix element. Second, it multiplies that strength by ρ of E final, which represents the density of available final states. A robust high transition rate demands both a strong physical interaction with the field and a high density of valid destination states waiting for the electron or spin to occupy them. What happens if you apply a perfectly resonant field continuously to a highly isolated two-level system? The probability population does not simply jump to the excited state and permanently stop there. Instead, the system engages in coherent cycling, a phenomenon discovered by physicist I. Rabi. This chart plots a Rabi oscillation. The external field drives the state population from ground to excited, but as the field continues to push, it actively drives the probability right back down to the ground state, repeating the cycle. This cycling grants us extreme precision control. By manipulating the field's duration, we can shut off the perturbation at an exact fraction of a cycle. If we cut the field exactly halfway through transition, applying a pi/2 pulse, the oscillation freezes precisely between the ground and excited states. This halted metric is a perfect coherent quantum superposition. The system exists in both states simultaneously. Rabi oscillations demonstrate that time-dependent fields provide a deterministic mechanism for writing and reading quantum logic. Taking perturbation theory out of abstract mathematics yields the blueprint for modern macroscopic engineering. Applying a time-dependent electric field governs atomic absorption and stimulated emission, generating all laser technology. Applying a time-dependent magnetic field drives nuclear spin flips measured in MRI machines. And meticulously timed microwave pulses serve as the exact Hamiltonian to execute logic gates on superconducting qubits. Despite their vastly different architectures, lasers, MRIs, and quantum computers all operate on the exact same underlying dynamic equation. Mastering the V of T operator allows us to move beyond studying stationary matter and begin constructing devices that rely on active quantum control.